University group, a NASA center, an aerospace company, Lockheed Martin, and so different cultural backgrounds. We have Canadians and Europeans, so it's quite a mixing bowl of different types of people, and we have actually learned to come together as a team. It's been a very wonderful experience to operate on Mars together.
The more we know about the oceans of our planet, the more we realize how little we know about the oceans of our planet in terms of mapping them, in terms of the life, in terms of many things. And I'm curious about whether your work filters back significantly in terms of oceanographic exploration, and what are the budgetary questions also, as a second question, involved in space versus here at home?
Talk about budget. Well, the ocean, of course, as you point out very eloquently, is virtually unexplored in some of the deeper areas. And one thing I think that relates to our Martian studies is we have found at the bottom of the ocean, several kilometers deep, where there's no sunlight penetrating, very dark, there's these black smokers. In other words, there's volcanic vents in the spreading centers of the ocean, and the volcanic vents are filled with sulfur. And there's an entire biosphere that surrounds these sulfur vents way down below the depths of the ocean at high pressure, away from sunlight. And it's really an incredible thing to see these absolutely outrageous creatures. I mean, they look like extraterrestrials, but they're kind of under-terrestrials, if you like, interterrestrials. As we learn more about these creatures, we find out that they're not living on photosynthesis at all. They're living on chemical energy, the energy of the sulfur in those vents. And that chemical energy is enough to give them all that they need for motion and reproduction and all the things they want to do. And we wonder on Mars, if creatures are living under the surface, maybe they have sources of chemical energy too. And that's certainly one thing we're looking for. As far as budgets, you'll have to talk to these gentlemen. I want more money too, of course, but they hold the purse strings.
Just to give you a perspective, the amount of money that was spent on Phoenix, amortized over, I guess it would be 6 or 7 years lifetime right now, is about $1.50 per citizen of the United States over the 7-year time span. And if you break that out per year, it's about $0.25 per person per year. And I would hope to think that an enlightened society needs to explore and to invest in many, many different technologies and to explore its outer solar system, explore the planet. And as Ramon said, perhaps one of the biggest payoffs is when we compare the information that we get from space exploration to the Earth. We learn a lot about the Earth, an incredible amount of the Earth. And that's probably where, as Peter used the word, the pay dirt is, at least now, for a lot of the exploration that we do.
So you could see Mars exploration as a green project.
Okay, thank you. Is there another question? Young lady over here.
How long does it take to get to Mars?
Well, getting to Mars depends upon when we launch, and there's usually a launch opportunity roughly every 2 years, what type of rocket we're launching on, and the exact place that we want to get to on Mars. For Phoenix, it took us about 10 months. But other missions that we've sent to Mars have taken either a little bit less or a little bit longer.
Question over here.
I was wondering how you're going to be testing the ice, and if you're going to be drilling into it at all, or what exactly you're going to be doing.
Well, that's a good question. One of our fears early in the development of this spacecraft was ice would be as hard as this tabletop, and your scoop would just scrape over it and not be able to pick any up. So what we did was designed a power tool to put on this scoop that actually is on the back of the scoop, and you put the back of the scoop down into the ice, and it spins like a rasp or like a circular file, and it throws chips into the scoop. So now we got just the right size of chips filling the back of the scoop, and we can dump them into our instrument. And the instrument we'll put them in is a little oven that's going to heat these things up. Of course, at the 32 Fahrenheit, we'll be melting the ice, and then, believe it or not, it's only another 8 degrees to have the boiling point on Mars. So at like 40 degrees Fahrenheit, the water will be boiling off, and we will be measuring its properties in our mass spectrometer. And then we'll be looking to see if this ice has melted and changed some of the soils around there, because you have volcanic soils on Mars. We're on the very kind of flank of a large volcano. And these soils are just straight out of the interior of the planet, never seen any water. And if they do see water, they can turn to clay, and they can turn to carbonate, and they can turn to sulfates. And it's those transformations that tell us that that ice has melted in the past. And if you find that in combination with organic materials, which may be protected in this ice layer, then you've got a habitable zone. And it'll be up to the next mission to tell us if it's actually inhabited, because it's a big area, and we only landed in one place.
Those of us that have long memories remember that was it in the mid-'70s, around 76, and I think we had another series of landers on Mars that also had marvelous little laboratories that did little scoopings. And in the 30 years since the Viking landed, what's happened to inform the design of your spacecraft to improve things? Now, what have you done that's different? What have you learned? What new materials have you been able to use, or new testing technologies that weren't around in the 70s?
Well, I think the big difference between our spacecraft and Viking was a huge project, multi-billion-dollar project, and they were very clever in their technology development, and they had the ability to send a lot of mass down to the surface, and they had nuclear power plants too. They were quite sophisticated, and for a low-cost mission, it's hard to compete with that sort of engineering talent. However, one thing we do have that they didn't have is we have knowledge of Mars. We know that where they landed is not a very likely place to find life. So I think the Viking mission had all the right tools. They just landed in the wrong place. And if they had landed where we are, who knows what the answer would have been back then, but it might have been quite different. And yes, there has been a lot of technological development. I think the entire 4 landers for the Viking mission has less computing power than my cell phone, and so we've learned a lot about miniaturizing technology and having more sophistication. But they did an awfully good job back then, and unfortunately they took too big a step. They said, what is Martian life like, before they even knew if there was any Martian life. And so they ended up with kind of a negative answer. Well, we didn't find any, so we don't know what it's like. So we're taking a little smaller step. We're saying, is there a place on Mars where life could exist? And once we find that place, then we'll send those instruments and their next generation back.
I think the important point is that the biggest difference was Viking really went there to look for life. We are not going there to look for life. We're looking to understand the history of the water and how that impacts us, and then how that also can impact future missions.
Another question. Well, while we wait for another question, I'll pose one to the panelists. The video you showed of the landing, coming down, and essentially a hard landing, that's not the way the rovers came down most recently with the airbags, which seems to be a much safer way of getting a spacecraft onto Mars. Why did